ये जो हमने सेकेंड टर्म लिखी है, सो यहाँ पर एक चीज मिस थी, यहाँ पर हम प्राइम लगाएं. सो वी आर गोइंग फ्रॉम द फर्स्ट इंटीग्रल टी नॉट टू टी डी टी प्राइम ओवर द स्पेस ऑफ टी t prime, and if we integrate over the space of t double prime, then we are going from t naught to t prime, because after integration of the second integral, whatever the results of the second integral, that would be integrated over the space of t prime. So the variable जो होगा लिमिट का सेकेंड इंटीग्रल में, अपर इंटीग्रल, अपर लिमिट, वो टी प्राइम होगा. सो दैट इज वाई वी हैव दिस अपर इंटीग्रल. नाउ इसी चीज को हम एक्सटेंड कर सकते हैं टू एन टर्म्स. And so we have this 1 upon n factorial term, which was basically integral from t naught to t. Remember हम ordering कर रहे हैं किसकी, Hamiltonians की at two different times. So we have t prime h of t prime, and this is whole to the power n. And so one can write this expression as the product of integral. So there would be n terms, n symmetrical terms. Symmetrical terms का मतलब है जैसे we symmetrize sort of operators. That is, if we have two numbers a and b, then we can write it as ab plus ba. So these are two symmetrical terms. और भी फॉर थ्री के लिए आपके पास अगर तीन वेरिएबल्स हैं तो देयर वुड बी सिक्स in fact terms. So the number of terms, symmetrical terms, would be, you can calculate with n factorial. So for two terms, टू फैक्टोरियल यानी टू टर्म्स हो जाएंगे, टू वेरिएबल्स टू टर्म्स हो जाएंगे. अगर थ्री वेरिएबल्स हैं, सो देयर वुड बी सिक्स सिमेट्रिकल टर्म्स. सो वी कैन राइट this integral for, or the nth term, as, so let's find out the cursor. So we have this 1 upon n factorial integral t naught to t, yeah, dt prime, then integral t naught to t prime dt double integral, double prime. Then we have integral t naught to t double prime, so dt triple prime, yeah, and so on up till we have an integral from t naught to t कितने primes, n minus 1, and this is dt n. ब्रैकेट में लगा रहा हूँ, इसका मतलब नंबर ऑफ प्राइम्स कितने, या सो जो अगर आप लिमिट्स का देखें तो यहाँ डबल प्राइम है, तो यहाँ सिंगल प्राइम है, यहाँ ट्रिपल प्राइम है, तो यहाँ डबल प्राइम है. सो इफ यू गो ऑल द वे टू द nth इंटीग्रल, then that would be dt over the space of n primes to integrated, upper limit integrated to t to the power n minus 1 primes, yeah. And then we would have those Hamiltonians in the last integral. And वो जो Hamiltonians हैं उनको आप जब लिखेंगे, so those Hamiltonians would be written as h of t prime, h of t double prime, h of t triple prime, so on. These are the product uh, of h of t n minus 1 primes, and so on, प्लस आपके पास टर्म्स होंगी सिमेट्रिक टर्म्स. ऑल द सिमेट्रिक टर्म्स. तो मैंने आपसे कहा ना कि इनफैक्ट ऑर्डर आपने बनाना है, एच ऑफ टी प्राइम, एच ऑफ टी डबल प्राइम, एच ऑफ टी ट्रिपल प्राइम. सो दिस कैन बी रिटन एज, अगर दो वेरिएबल्स हैं तो यानी ए कॉमा बी, दो वेरिएबल्स हैं तो इनका 1/2 फैक्टोरियल नॉर्मलाइजेशन कांस्टेंट. सो दिस वुड बी ए बी प्लस बी ए. एंड अगर तीन वेरिएबल्स हैं तो देन यू वुड हैव द नंबर ऑफ टर्म्स जो होंगी वो ए बी प्लस ए पी सी प्लस ए सी बी प्लस बी ए सी, एंड सो डिफरेंट अरेंजमेंट्स आपको डिफाइन करनी होगी. सो that is what we meant by this symmetric term. So not just these this arrangement, but all those arrangements of this h of t. Yeah. And so so to get u dot, क्योंकि again हमें इसको satisfy करना u dot of h of t into u, uh, so one needs so one needs to reorder reorder the terms in this bracket term, ये जो bracket term, yeah, one needs to reorder them in this bracket term such that h of t prime such that h of t prime is always on the left. Why on the left? Because this is the starting point, the lowest time on the left. Yeah. So on the left, so we go from the lowest time to next time, from the next time to still the next time, from the next time to still the next time, and so on. So h of t जो है, h of t prime जो है, it has to be on the on the left. So solution क्या होगा? We need to have some sort of time ordering, yeah, or time ordering operator. So uh, solution of this requirement is by reordering as time ordered unitary operator, that is u of t comma t naught is equals to summation over n integral t 0 to t dt prime integral t 0 to t prime dt double prime, so on up till integral t naught to t n minus 1 dt n times h of t prime h of t double prime, so on h of t n minus 1 prime. ठीक है, n minus 1, number of primes are basically n minus 1. So this is basically time ordered, that is time ordered arrangement. We have this time ordered arrangement, और इस टाइम ऑर्डर्ड और पाथ ऑर्डर, इसको टाइम ऑर्डर्ड और पाथ ऑर्डर भी कहते हैं. दिस इज ऑल्सो नोन एज path ordered. अच्छा, we have so u of t comma t naught, this would be some path order operator. So since we need to order these Hamiltonian into some time sequence or some arrangement, so we need to have some time ordered operator. So यहाँ पर हम p जो है एक ऑपरेटर इस्तेमाल करते हैं, एंड सो वी कॉल इट एज सो जो एक्सप्रेशन है सेम रहेगी, सिर्फ क्या होगा कि हम एक टाइम ऑर्डरिंग ऑपरेटर इस्तेमाल करेंगे p, जो इनफैक्ट इन हैमिल्टोनियन को फ्रॉम स्मॉलेस्ट टाइम टू द नेक्स्ट टाइम टू द नेक्स्ट टाइम और टिल द हाईएस्ट टाइम तक लेकर जाएगा. सो वी वुड हैव माइनस आयोटा ओवर एच बार इंटीग्रल टी नॉट टू टी वट एवर. इस टी नॉट टू टी के अंदर वो सारे इंटीग्रल्स मौजूद हैं. सो फ्रॉम टी नॉट टू टी, फ्रॉम टी नॉट टू टी प्राइम, फ्रॉम टी नॉट टू टी डबल प्राइम, फ्रॉम टी नॉट टू ट्रिपल प्राइम, सो ऑन अप टिल टी नॉट टू टी एन माइनस वन प्राइम्स. या एंड सो हम अगर इसको एक्सपोनेंशियल नोटेशन में लिखेंगे So this comes out to be the same dt h of t prime n bracket close. So this is basically path order or time ordered exponential. So इसको हम कहते हैं path ordered or time ordered exponential. Yeah. So that is basically, uh, in fact, something which is in general setting, and this does not just apply to quantum mechanics. Then you have some path that one needs to integrate along and just order the operators so that they are always in an increasing order of time. One could say that. So in general setting, let's say in general setting, that is in general, what we can say in applying uh, not just not just to quantum mechanics, then you have not just in quantum mechanics means you can also talk about particle physics as well. So it is this type of arrangement. It is not just specific to quantum mechanics, but it is also specific to other, in fact, disciplines in physics. Not even just to particle physics, but also to other, just for example, condensed matter physics. So we need to have a setting where the time is ordered. That is, we go from smallest time to next time and so on. Then you have some path that one needs to integrate along and just order those Hamiltonian, order those Hamiltonian operators, order the operators so that they are always in some correct order of time, in an increasing order along the buck. So you could always think about. So uh, in fact, अब आप गौर करें तो वी आर बेसिकली यूजिंग द श्रोडिंगर पिक्चर, एंड सो जो सोल्यूशन हमारे पास ये आया है यू ऑफ टी का, रिमेंबर हम लास्ट टाइम से या उससे भी लास्ट टाइम हम बुनियादी तौर पर श्रोडिंगर इक्वेशन का सोल्यूशन निकाल रहे हैं, या सो वी कैन से ये एक मोस्ट जनरल सोल्यूशन है श्रोडिंगर इक्वेशन का जो आपने निकाला ऊपर, ये पाथ इंटीग्रल नोटेशन के अंदर ये जो सोल्यूशन हमारे पास आ रहा है, दिस सोल्यूशन of Schrodinger equation is the most general solution of the Schrodinger equation. So one would say mm, this is the general solution of Schrodinger equation. और ये जो पाथ ऑर्डर्ड इक्वेशन है, इसको पाथ ऑर्डर्ड इक्वेशन भी कहते हैं, इसको डायसन सीरीज भी कहा जाता है, बिकॉज ये एक मैथमेटिशियन है जिसका इंतकाल हो गया अभी 2006 में, आई थिंक, फ्रीमैन डायसन, जो जिसने इसी को इस्तेमाल किया था या इसी अप्रोच को इस्तेमाल किया था इन पार्टिकल फिजिक्स. सो दिस पाथ ordered equation is also known as Dyson series, uh, because it was also used by Freeman Dyson in his in his discussion in his discussion about particle physics on particle physics. Or why it is useful in particle physics? So you can think about the evolution of different constituent particles, and that evolution is basically the evolution in time. So we could think about, we could imagine some big Hamiltonian and some small Hamiltonian, so that one piece of Hamiltonian describing harmonic oscillator that can be solved, and the other piece cannot be solved unless the first piece is solved. So the first piece is solved, then you can solve the second piece, and so on. And then in some perturbative sort of way or perturbative scheme as a solution to Schrödinger equation. Yeah. So so one can imagine, say for example, you turn off these small perturbative pieces and gradually turning it on. यानी आप पहले off करें और gradually turn it on करें. And as you solve the equation, you turn on successively in time to get the solution. Yeah. So बिल्कुल ऐसा ही है कि you have primordial soup at the start of the universe, and which is some initial time, maybe whatever the time, and then that primordial soup precipitate. So we have some small perturbative scheme because of which there is some sort of precipitation, and those precipitation would result into quarks. And then we have these quarks. These quarks then somehow, in some small perturbative scheme, sort of combine to become hadrons, that is protons and neutrons. And then those protons combine with leptons, that is electrons, to form some composite particles such as hydrogen atom. And then those hydrogen atom combine to form hydrogen molecule, and so on, till you have those stars and galaxies, and me and you and everything. So this is all is this all these perturbative Hamiltonians, they are time ordered. So unless you have solved the preceding one, you cannot solve the later one. So you have to solve the first, you have to solve the preceding Hamiltonian. Once you have solved the preceding Hamiltonian, then you come to the next, and then you come to the next, and then you come to the next, and so on. So if we have a quantum mechanical problem and is solved using Schrödinger equation, then that is the most general solution of a Schrödinger equation, which is this unitary operator as a time ordered equation. So this is something which is very important. Yeah. Uh, then we let's return. So this is जो those two हमने कर लिए, यानी हमने केस वन किया जिसमें हमने टाइम इंडिपेंडेंट हैमिल्टोनियन की बात की, और फिर देन हमने केस टू किया जिसमें टाइम डिपेंडेंट हैमिल्टोनियन की बात की. फिर टाइम डिपेंडेंट हैमिल्टोनियन के केस के अंदर भी हमने दो सब केसेस किए. एक वो केस किया जिसमें हमने हैमिल्टोनियन और यूनिटरी ऑपरेटर को हमने नंबर्स माना, और देन इन द सेकंड केस वी say that those Hamiltonian operator and the unitary operator are not numbers but operators, and we reach to some general solution of Schrödinger equation, which is the time ordered equation. Now let's return to the time independent Hamiltonian, and write the Schrodinger equation and see whether there is some other way in which the solution to physical problems can be obtained. That is, instead of using Schrodinger equation, can we solve the physical problems in some other manner? So इसको देखते हैं. But let's return to the case of the time dependent. So consider the time independent Hamiltonian. Yeah, and in that case, eigenstate eigenstates of Hamiltonian can be written as h. Those can be written as h of En, which is equals to En En. These are the eigenstates of the Hamiltonian. So to solve the Schrodinger equation, one need to have some sort of a wave function, yeah, at time t0. So इस equation को solve करने के लिए, which is the Schrodinger equation, uh, so to solve the Schrodinger equation, which is time independent Schrodinger equation, one need to one needs to have the wave function at t is equals to 0. So at t is equals to 0, the wave function would be psi comma 0, which is equals to summation over n uh, En, which is the probability amplitude, psi comma 0. That is the overlap of that is at time t is equals to the system would be in some lowest state with energy En. ये इसका मकसद है इस overlap का, time the state En. Yeah, and this is written as psi of t, that is at later time. So this is at time t is equals to 0. This is at time t is equals to t. So at later time, this would be you defined by the time evolution operator e to the power minus iota ht over h bar time psi comma 0. So this is the wave function. Wave function at time t is equals to 0, and the wave function at some later time, which is t. Yeah. And so one could then in fact write this equation as, this can be written as e to the power minus iota, और पहले आप वो फैक्टर लिख दें. सो अगर मैं सब्स्टिट्यूट कर दूं किसकी वैल्यू, if you substitute the value of this, the wave function at time t is equals to 0, then that would be summation over n En psi comma 0, and this would be e to the power minus iota h t over h bar En. Yeah, so this is basically the wave function at some later time equation. And these energy eigenstate En, they are basically referred to as the stationary state. So these energy eigenstates En are referred to as stationary states. Yeah. So, and why they are called stationary states? So, so if psi starts out, if we start with the psi, let's say some state psi, which is proportional to one of the eigenstate, then it will remain proportional to that eigenstate, possibly multiplied by some phase factor. Yani, it would remain in that state, and the only only changes would be some uh, phase changes, and so we could just write the phase factor, but that would remain in that state, and that's why we call it as the in fact stationary state. So. Um, in fact, this is basically some in fact solution for the Schrödinger equation. So, uh, but then uh, अभी तक जो हम बात कर रहे हैं वो हम ये बात कर रहे हैं कि in fact the wave function is a function of time, whereas the observables are independent of time. There could be a case where we think about the observable, that is, for example, an observable A. In Schrödinger picture, observable A is not a function of time, whereas the state function is a function of time. In some other, in fact, arrangement or picture or paradigm, you could think about state function as not a function of time and observables are function of time. And such a paradigm is known as the Heisenberg paradigm or Heisenberg picture. And so we need to drive Heisenberg equation of motion in the next